I'm
No, I've been out of town
Oh,
for
have
a
you?
couple of weeks.
President of Story.
I'll pay you later.
And we'd like to thank all of you for coming tonight. We feel this is a very pertinent subject, and we're glad that you're taking an interest in it. We would also like to thank our 4 panelists and our moderator for taking time from their very busy schedules to come and talk to us. We feel that we have assembled a very qualified and very distinguished group of men here to talk to us about this subject. So at this time, I'll turn the meeting over to Howard Bell, but just before I do that, I wanted to explain that WOI is going to take this program to air sometime today. So at the end, we will have a chance for questions, but we will break for coffee, and then they would like to have you write your questions down on paper, and then we'll give them to Howard Bell, and he will ask the 4 panelists the different questions. Then this way they can get it all on tape. So this time, Howard, would you like to introduce our panel?
Well, thank you very much, Gladys. Ladies and gentlemen, tonight we're very fortunate to have a distinguished panel on hand to discuss the topic, the energy crisis. Just a couple words of introduction here. Energy is an absolutely essential facet in the welfare of the United States. And the reason, of course, is that all human life depends upon energy, and this nation could not possibly live without it. Dr. Glenn Seaborg, the former head of the Atomic Energy Commission and the 1972 president of the American Academy of Science, put it succinctly when he stated, quote, "The future of energy is the future of man. Without it, we become nothing. With it, we become whatever we wish and strive to be." And it's doubtlessly no mere coincidence that there is a relationship when you're comparing groups of nations to note that less than 50% of the world's population consumes close to 90% of the world's energy. And there's a great chasm between the advancement of the energy-using natures and the non-users. The greater the power consumption per year per capita, the greater the life expectancy and literacy of the populace, not to mention the overall prosperity of the nation and the growth of national product. It would appear then that denied a sufficient supply of energy, a developed country could progressively backslide to a more primitive state. Now today we're confronted with a situation in which a total lack of energy is certainly not a realistic prospect for this country, but we are confronted by an actual inadequacy of supply at the present time and a growing potential for shortages in the future. And to many experts, our energy future looks rather bleak right now. Representative Craig Hosmer of California is the most prospective congressional observer of energy matters, likens our problem to that of a man who, having jumped from the floor of a 40-story building, the 40th floor, casually observes as he passes the 20th floor that things still look pretty good. But upon reaching the 10th floor, he observes that the problem is beginning to look rather serious. The bottom line of Representative Hosmer's analysis is that the nation's energy problems have now reached about the 5th floor. Now, how did we get here? How do we avoid a crisis? Well, our panelists will view the problem and offer possible solutions from varying points of view. The first panelist tonight who will address you is Dr. Glenn Murphy, a man with whom I've had many pleasant years of experience. I was on the staff at Iowa State University. He's a distinguished professor of engineering at Iowa State University. He's the head of the Department of Nuclear Engineering, and he's the author of many articles and books in a wide range of engineering topics. And he's been honored by national engineering societies for his contribution to the overall field of engineering. Without further ado, Glenn, I'll turn it over to you.
Thank you, Howard. As Howard has pointed out, there is a serious deficit of energy approaching. And this comes about simply because we're using more energy. Sometime this morning, probably every one of us flipped a light switch. And the light came on just as it did a year ago. But one thing is different, and that is that there are more people, and all of the people are wanting more power. The net increase has amounted to about 7% in the last year, and that rate has been going on for many decades. Not much. 7% increase is not much, and we rather get used to a a 7% increase. But this means that the doubling time of energy requirements is about 10 years. This means that in 1983, we'll need about twice as much power as we did today. In 93, we'll need 4 times as much. In the year 2003, we'll need about 8 times as much energy. This is based on the data that have accrued in the past and includes both the population increase, which is about 1 3/10% per year, with additional births, death rate being lowered somewhat or greater age of living, and immigration entering. In the present rates, this means that the city of Ames would require the equivalent of 16 of the present power plants that we have within the 30-year period. If you look in the phone book, you will see that we have a municipal plant that added to its capacity in 1958, and again just 10 years later in 1968, it was approximately doubled, just a little more than doubled in that 2-year period. So by 1978, we will expect it to be doubling again. Last time it cost us $8 million to double the size of the power plant. You can assume that it's going to cost something the next time we add to it. This has been going on all over the United States, so that the average has amounted to 7% per year. And as I said, this comes about because there's greater power use per capita. When I was growing up in our home, there were 4 light bulbs in the house. That is 4 drop cords from the ceiling, and we had about 40-watt lights in each one of these and never had more than 2 of them on at the same time. Well, the situation's quite different now. In our house, we have something over 50 electric motors associated with different parts of the house. So this particular thing is not unique to us, I am sure. Now, how are we going to accommodate the increase in need for energy? Well, one way, of course, is to keep right on building power plants the way we have been. If we continue this at the present rate, and there's every reason to expect that the present rate will continue, by the year 2003, or 30 years from now, this will mean that we need to build more than 10 times as many electric power plants as the total of those constructed in the past 67 years. New construction will amount to something over 2 million megawatts of electrical power. Now at 400 megawatts each, this would be something in the order of 5,000 new plants that would need to be built within the next 30 years. The Iowa quota of that would amount, of course, to about 100 plants, or approximately 1 large plant per county. This construction would mean that we would need something over 6 million man-years of effort simply to build the plants alone. This would require about 200,000 men working full-time for 30 years. Now, when you consider that our present labor capacity is only about 50,000 involved in this kind of labor, you'll see that we have some difficulty in getting the power plants constructed, let alone fueled and operated. If we look at the fueling that might be involved in these, we can think of several different things that may be used. Of course, fossil fuels are the first ones that come to mind: coal, oil, and gas, because these have been used in the past for a considerable extent. And some of the other panelists will be talking more in detail about those, so I will simply pass over that by mentioning that we have problems in connection with coal production because of the strict mine laws that have gone into effect and because of the difficulty in locating sources that are cheap and which are low in sulfur content. The oil problem is one which is confronting us at the present time. You talk to anyone out in Pammel Court within the last month, and they will have things to say about the oil supply. Gas, we know, has some problems, mainly economic, associated with that. If we look at the other sources of power, we have hydropower, and we do not have much more potential for the development of hydropower within the United States. This certainly will not, by any stretch of the imagination, begin to take care of the needs in the future. Another possibility is wind power. 30, 40 years ago, one would see windmills scattered all over this part of the country to help to supply some of the power need and to help with the production of electricity in some cases. Now, the difficulty with this is that wind doesn't blow consistently, and it doesn't always blow at the time we need the power. So it does not look at the present time as though this would be a very dependable source of power. Tidal power is another one which can be utilized theoretically. The tidal power, however, is very expensive to develop according to all estimates that have been made. And it means that the power would be developed at the seacoast rather than being available economically to the interior of the country. Thermal power in the sea is one on which some experimental work has been done. The French have developed some electrical power by utilizing the difference in water temperature between the surface and the depths of the sea. Geothermal power, or utilizing the power coming from the greater heat down in the depths of the earth, is used effectively in certain locations. In Iceland, for example, they are using geothermal power to heat all of the buildings in the city of Reykjavik. We've been using geothermal power as well in California in some places. It is available in quantity in New Zealand and has been used in Italy for many years in a portion of northern Italy. Solar energy has been talked about somewhat. In connection with that, we have two principal problems. One of them is storage of the solar energy, the fact that the sun doesn't shine at night, and the other problem is one that of the overcast that is frequently present, so that this, coupled together with the fact that there is a very low efficiency in the production of electricity from solar energy, means that it is not a very effective method at present. Someone has calculated that it would be necessary to utilize essentially all of the state of Arizona as a solar collector in order to provide the power that is used, that would be used in the United States by the year 2000. This is not very practical. The other thing that could be done, of course, would be to build a solar collector, put it out into space where it wouldn't take up any of the Earth's surface, and then beam the energy back to the Earth. Well, in view of the fact that we sometimes have difficulty getting power from the Ames plant downtown out to the 3rd Ward, I'm not quite sure that we could dependably get all of the power back from a station out in space somewhere. So we need to look at some other things. Well, as you might have guessed from the introduction, one of the other possibilities is nuclear power, and I'd like to say just a few words about that as well. And that is that nuclear power has certain advantages on the face of it. That is the advantage of having a large amount of energy available with a small amount of material. A pound of uranium fully consumed as fuel will be equivalent to a long train load of coal. And it also has a potential for producing more fuel from non-fuel materials than it utilizes. Put in other words, what I'm saying is that we can take a pound of uranium, utilize it completely to get the energy out of it, theoretically at least, and at the same time produce about 1 3/10 pounds of new fuel. Now this is the ideal to which we are striving. At the present time, it is actually possible to produce more fuel than is being consumed, and at the same time produce large amounts of energy from the fuel. This is with the fission devices that we now have. With the fusion devices that are being considered, but which have not yet been engineered to the point of actually producing fusion power in quantity, it would be possible then to produce about 8 times as much energy as is produced per pound of the present uranium fuel. Another advantage of the fusion device, when this is developed, and I'd look for its development within 50 years at the outside, we would then be able to utilize seawater as one of the sources of energy. Some of the constituents of seawater could be utilized as the fuel, and there would be adequate fuel capacity for many years to come. So far as the problems about nuclear energy are concerned, first of all, let me say that many of these problems have been overcome so that nuclear energy is being produced cheaper than its competitors under certain conditions. The safety of the nuclear plants is well demonstrated. It is the safest of the industrial operations that we know about. This comes about as a result of a great deal of care in the development of the plants. The licensing arrangements are very complex, and compliance is checked on regularly. Radioactivity coming from the plants has been a source of concern to many people, both inside the industry and outside of the industry. The facts are that there has been sufficient concern within the industry that the radioactivity levels have been held very low at the outside of plants. A jet flight between Des Moines and Los Angeles will subject a person to more radioactivity than they would be subjected to by being on the outside of a nuclear plant for 4 months, day and night. The waste disposal problem is another one that is getting considerable attention at the present time. This, I think, is going to be one which we will solve by the very simple expedient of making use of the waste products. Up to this point, it has not been particularly economical, or people have not been particularly interested in utilizing the waste products. But as with most everything else, we can find uses for these. And this, I think, is going to be the ultimate answer on waste disposal. Well, in summary, because my time is about up, I would say that all indications are that we will need about 8 times as much energy within 30 years as we are using at the present time. Providing for this energy is going to strain our construction capabilities. It is going to give us difficulties concerning the obtaining of adequate fuel and the distribution of this. The solution, I believe, ultimately will be to use a mixture of fuels, with nuclear coming into the picture more and more. And I have full confidence in our ability to solve these problems as time goes on. When we need to solve a problem, we can usually solve it.
Thank you. Thank you very much, Glenn. Your remarks are certainly very interesting and informative. Our next panelist is Dr. Carl Vondra. Carl is Professor of Geology in the Department of Earth Science at Iowa State University. His discipline is stratigraphy, and prior to coming to Iowa State University, he was employed as an exploration geologist for both Chevron and Amoco corporations. Carl?
Thank you, Howard. Let me adjust my slides here a
be
moment.
just
Mine
fine.
are at the end of the tray.
The lights off,
That would help.
oh, that helps.
Well, indeed, there is an energy crisis, and it's not one that was created by the petroleum industry. I'd like to talk to you about petroleum. There is still a great deal of petroleum to be found, in fact, enough to satisfy our needs for a few years. And it is petroleum that is our main source of energy, petroleum, which would involve oil and gas. These are fossil fluids that occur trapped within the rocks of the Earth's surface. You notice here that the demand is very great. It's surprisingly great, in fact. And this is fairly recent. You can see January 15th, and it has to do with statistics for the week of January 5th. 18,193,000 barrels of oil per day are used in this country. That's of that particular week. And that's up 1,956,000 over the previous year at the same time. And the figures for the past week, fortunately I didn't have an opportunity to make a slide of those, are up 200,000 barrels per day over a month ago. So you see our need or demand for this kind of energy is increasing, but our supply is down. The supply, as of a month ago, the week of January 5th, was 12,035,000 barrels per day. And that involved a number of things. It involved domestic crude production, which was 9,400,000 barrels. It involved crude imports, which have been increasing. And it involved product imports. These are petroleum derivatives that are imported from Europe and from the Near East and South America. And then, of course, the crude which runs to the stills from sources that we have domestically here. I'm sorry, I gave you the wrong figure there. I actually should have added these together. Should have been 13 million and some, about 14 million. So you see we're running behind. I took this as a total. So the total should actually be these three figures here for our actual supply. So our supply is running behind our demand. Now we have stocks, however, and our stocks are significant, but of course they wouldn't last too long at the present rate that we're utilizing the oil. And here are our stocks. You can see that our crude on hand that we have is 242 million barrels, or 243 million barrels. And we have quite a stock of gasoline and quite a stock of middle distillates, and these are the fuel oils that we've been so concerned about here recently. It has been this that has brought our attention to our energy crisis and, of course, the shortage of gas. The next line, please. Well, that crisis definitely exists, and it's because we don't have enough petroleum on hand at present. This gives you some idea of how much petroleum has been found in this country since the first oil well was found in the 1850s. And there has been, of course, an increasing demand for that oil. At first, the first 50 years, it was very difficult to get rid of it or to sell it. And it was sold primarily as medicines and elixirs, but gradually it replaced the whale oil business. In fact, it caused the death of that industry. And it took over as a lubricant and then eventually as a primary source of fuel, of energy. Well, this is how much is left to be discovered. 810 billion barrels left to be discovered. Actually, that's not quite true. The total amount that will be discovered, that includes the amount that has been discovered and the amount which is discoverable. And here's the same for gas, natural gas. This is the amount that has been discovered to date. This is the total amount which will be discovered from the first time that we began utilizing natural gas. This is the amount that remains to be discovered. So you see there is still, at least in natural gas, a sizable amount to be discovered, and the same is true with oil. But our increased demand, however, is making this amount a very small one. And we can make predictions up to 1985, and it looks still pretty good for petroleum. Let me have the next slide. The big problem is the fact that we haven't been carrying on exploration the way we should have to find this petroleum, and there are a number of reasons for that. One of our greatest sources or areas which provide a source for petroleum is the Gulf Coast region offshore. It provides daily about 1.6 million barrels of oil, which supplies a good share of the petroleum we use in this country. The rest of that 9 million comes from the interior here. However, we have not tapped, of course, this area up here in Alaska. Well, looking at the offshore region, most of the oil is coming, well, all of the oil is coming from the continental shelf area, an area that varies in depth from sea level to 600 feet below sea level. Thus far, we've only explored 2% of our continental shelf. So you see we have a good share of our continental shelf area here, and that's all in this darker blue right here, to be explored around our continent of North America and a good deal around the United States itself. Some of the areas that hold great potential, of course we know about the Gulf Coast here. It's subdivided into 3 areas, the greatest one being the central region, but this one is just now being looked at, the eastern Gulf Coast, and it looks like it will have equally as great potential as the central Gulf Coast. The southern Atlantic, the central Atlantic, the northern Atlantic, all will be important, and of course this area north of Alaska will be very important. Our entire west coast shows a great deal of potential, including, of course, that area off Santa Barbara, which now has been off limits for a couple of years for drilling as a result of an accident there, a drilling accident which resulted in the leaking of oil. There are onshore many good areas to search for petroleum that are remaining. However, they are becoming very expensive because the obvious areas have been explored. This requires drilling to depths of 20 to 30,000 feet, and that is very expensive. Just recently, the deepest well drilled in Oklahoma just a year ago went to 30,500 feet, and it was in search of gas, natural gas. They found gas at 18,000 feet. The gas potential of that well is about 200,000 cubic feet of gas per day. And the cost of gas today, the average cost of the wellhead to the fellow that found that oil well or gas well is 17.1 cents per 1,000 cubic feet. So you can see that makes that well just marginal when you consider that it costs $6 million to drill the well alone, and that doesn't take into account the expense involved in exploration. The Anadarko Basin, which is in southwestern Oklahoma and in the panhandle of Texas, is one of these deep gas basins where the average wells are being drilled to 20,000 feet. And it holds great potential for natural gas and will provide us with, estimates are anywhere from 50 to 100 trillion cubic feet of gas. To date, it's only provided about 11 trillion cubic feet of gas. But it has great potential, but it will be very expensive to drill to those depths, and at the present cost for gas, which is fixed by the FPC, it's not profitable to really go out and search for it. So there you see what the potential is, at least. I have a few things that I've written down here that I think need to be done if we're going to get some of this energy. Of course, it's not everlasting, as you can see. First thing we're going to have to do is coordinate our national energy policies. There are some 60 agencies, government agencies, that are involved in energy one way or another, and there really is no coordination between them. Second, we're going to have to establish realistic environmental, health, and safety standards that involve the search for energy. Of course, this will require some protection for the environment. That is an important concern, but at the same time, I think there will have to be a balance between environment and our search for energy. Third, we're going to have to encourage a greater development of resources on public lands, and this is a real problem. About 50% of our remaining oil and gas potential is on public land, and that includes these continental shelf areas that I mentioned to you. By the way, I didn't mention the continental slope area, which has not been searched at all, and that's the region from 600 to 6,000 foot depths beneath sea level. That has not been looked at all. Well, just recently there was an offshore sale of land, government land, and just a very small parcel was put out for sale, and those sales are about yearly. That small parcel of land brought on closed bids $1.6 billion, which went to the federal government. Well, that $1.6 billion could have drilled all the oil wells, wildcat wells, and production wells that were drilled during the previous year, during 1972, or during 1971, actually. It was during 1972 in September that this sale was held, and it was for offshore Louisiana lands. So you can see what part of the problem is. The oil companies are paying so much just for the opportunity to drill in the area to the federal government that there just isn't enough capital left to do the necessary exploration. And then such small parcels are let out for sale. The same is true for coal and uranium. 40% of the coal is on federal land, 50% of the uranium on federal land. About 85% of the oil shale and tar sands, which may be very important in the future, are on federal land. And of course, the chart that I showed you here involves the recoverable oil, the free oil, not that which is trapped within shales or trapped within the tar sands. And there is almost as much trapped in that as was shown on that chart. For instance, in the tar sands of Canada, there are, and these aren't estimates, they're actual figures, 800 billion barrels of oil tied up in the tar sands. The Shell Oil Company will have the first refinery operated there in 3 years. It will recover 300,000 barrels.
Another one,
per year.
fifth point is to maintain the oil import
Quotas, and I think we all know the reasons for that. The more oil imports we bring into this country, the less likely we're going to search for oil here. Now, you might say, well, let's go find our own oil and not produce it. Let's go ahead and import oil from foreign countries. It just doesn't work that way. When you put $6 million into a well, you want to get a return on that investment. You can't afford to let that $6 million sit there for 15 years. Now, perhaps the federal government could do that, but industry cannot. So it would discourage our own exploration and make us dependent upon foreign countries, many of which are very difficult to deal with politically. Sixth, we should allow field prices of natural gas to reach their competitive level rather than placing a arbitrary level of 17.1 cents, which is the average price at the wellhead per 1,000 cubic feet of gas. And the prices vary from 5 cents per 1,000 cubic feet, controlled by the federal government, all the way to 40 cents. 40 cents right now is more realistic. This wellhead price was set arbitrarily in 1958. And finally, we should expand research. Industry, of course, does carry on a good deal of research, but it varies with the amount of capital they have to deal with and the profit they're making, and in the last few years, the profit hasn't been good. I might add that the industry is planning a big exploratory effort this next year. They are budgeting a record $10.2 million for exploration.
Actually, for exploration and production, refineries, etc., 5.8 billion will be for exploratory drilling and exploration. And it will result in about 32,000 wells being drilled, which will be a record. The last time they came close to that was in 1969. That's assuming, of course, it will be a record. That's assuming they have some success, because that's important. The more success you have, the more initiative you have to search for oil. Well, thank you.
Well, thank you, Carl. Your remarks were very interesting and gave us a good deal of food for thought. Our next panelist is Dr. James J. O'Toole. He's a physiologist, associate professor at Iowa State University and Vet College, an associate at Ames Lab. He's an ecologist in the area of radiation and chairman of the Environmentology Council at Iowa State. Jim will give us an environmentalist viewpoint of the energy crisis. Jim?
Thank you, Howard. Well, the energy crisis we face now, and inevitably in the future, casts a double shadow. The one we see clearly now outlines the dilemma of the near future and our problem in finding energy sources to supply our needs for direct use in heating, transportation, electrical generation, in keeping industry and agriculture going, living in the manner, no doubt the grand manner, in which we become accustomed. Needless to say, our technological society now consumes more energy per person than any other nation, over twice as much as Sweden and other Western European nations. In a relatively short period of time, we have come to experience a domestic shortage in petroleum, with future projections showing greater demands for imported oil. Since the early 1950s, our per capita consumption has doubled. Our appetite for electricity is even greater. Here, our doubling time per capita is 10 years. And what's more important, this rate of increase has been predicted to continue. And I wonder if you appreciate just what doubling time means. To mathematicians, it's called exponential growth. And I like to illustrate it in this way. A fellow living in the country has a lily pond. At least it will be a lily pond. But on day one, the 1st of May, he wanders around and spots a water lily down in the corner of the pond. And the second day, he sees 2. And the third day, he sees 4. And in the 4th day, he sees 8. He takes a trip and comes back on the 29th day and notices that his lily pond is half covered. And I wonder how many days he has left before it's completely covered. He's got 1 day. To understand the impact of any exponential growth rate is to understand the problems that we face in the future, and the very near future. One report states that if this rate continues, we'll run out of power plant and transmission sites about the year 2000, 1 generation away, and out of land and water space by the middle 2000. Unfortunately, there are other severe considerations that may have escaped serious scrutiny. And to interject a reflective note, let me ask the obvious question: what are we going to do with all this energy? Well, we have reached a lifestyle now that's based to a great extent on the culture of waste. How can our environment really tolerate any more of this approach, imagining a quadrupling and a quadrupling of that in the early 2000s? More importantly, where will the raw materials come to which this energy will be applied? Right now, 6% of the world's population, we use over 30% of the world's resources. I think you can see the relationship now between natural resources and energy. This energy has to go someplace. The environmental impacts of energy use are directly related to the per capita consumption of energy. For example, our annual health and property damage bill for air pollution alone is $16 billion, of which $6 billion is assigned to fossil fuel power plants. And this is in the Council of Environmental Quality's 71 annual report. If we prorate this cost per power plant, it would about equal the cost of the mortgage payments on the average fossil fuel plant. But getting back to resources, the industrial productivity of this country has resulted in a great drain on our own natural resources as well as the world's. We import over 90% of aluminum and chromium ores, 65% of nickel and tin ores, and over 30% of iron ores, our main resource, non-renewable. We live on a spaceship Earth, and as the cliche goes, we recognize that everything has a limit. To emphasize this, here's a few statistics which estimate the current supplies of global resources. And these are from the U.S. Bureau of Mines Mineral Facts and Problems resume, an official publication. And these supplies are, I'll quote these on two bases. The length of time they will last based on the exponential use of energy, and the length of time they will last provided we level off at our present rate of consumption. In aluminum, at a constant rate, it would last 100 years. At an exponential growth rate, 31 years. Iron would last 243 years, 90 years exponentially. Chromium, 420 years at a constant rate, 95 exponentially. Lead, 26 at a constant rate, 21 exponentially. Nickel, 150 years, 53 exponentially. Natural gas, 38 years, 22 years exponentially. Petroleum, 31 and only 20 years exponentially. Copper, 21 years exponentially. Zinc, 18 years exponentially. Obviously, if we could find a genie's lamp like fusion power, we still would be stuck with our limited Earth and its short supplies. The long shadow portends even more. These productive ventures produce pollution. Every increment of productivity leaves its impact on air, water, and land. We shouldn't be deluded with the public utterances that energy will solve the pollution problem. There are, of course, action-forcing programs that will minimize environmental impact. But these must be anticipated and integrated with the growth phenomenon. And we're way behind right now, as that statement that was published on the health effects of air pollution. When I say integrated, I mean we have to view our system in its holistic aspect. That energy is not something to be considered separately from resources and separately from the environment in which we live, and even separately from our own personal desires and wants. And we're getting pretty fundamental when we reach this level of consideration. We may even by now begin to visualize a model emerging from our manner of life, our day-to-day demands, and relate this to the limits imposed by the Earth itself, just as the natural world is limited by its energy source and by its natural resources in the soil and in the water. We need to consider this, both our physical limits and our psychological limits, in order to survive. We live in a nation where the public has come to accept the fact that decisions which are vital to society are being made almost exclusively by institutions and governments. In our present dilemma, we should ask one another whether or not these present institutions are serving the public. And if not, what is needed in the way of reorganizing public institutions to achieve their proper end? In order to answer this key question, the public will have to agree on what is a public interest and set goals for the nation's future, not just until today's fuel crisis is solved or gets Band-Aid treatment, but the long, long pull into the future with the understanding that when the decisions we make today on energy and resources will have its impact on the quality of life for our grandchildren and their great-grandchildren. The year 2000 is only one generation away. To set our goals, we as individuals need to learn a great deal about energy and about our store of resources, which is all we have on this spaceship. Perhaps our first lesson, the fuel crisis today, has made its impression. We know now that these factors have limits. We have to learn a great deal about the relationships of energy to our society and its complexity. Early pioneers, for example, knew at a glance at the woodshed or a look out the back window at the woodlot what was in store for the coming season. Now we rely on a complex supply system with options and decisions being made by others far removed who frequently disagree among themselves and who have vested interests other than the public interest. It's time we tried to close this knowledge and information gap. It's apparent that our institutions, which are charged with responsibility for coordinating allocation, use of energy and resources, are also in a state of confusion. Energy crises were predicted 20 years ago by resource analysts and demographers. The public today is clamoring for a national fuel and energy policy, and there is none yet visible. The significant cause of this dilemma is a division of responsibilities among government agencies, all with separate missions. For example, the Department of Interior has long had the mission of developing coal and oil resources of the nation. The AEC has had the mission of both promoting and regulating the development of nuclear power. The Bureau of Reclamation and the Corps of Engineers has had the job of damming rivers and developing hydroelectric sources. These roles were set when the nation was conscious of its great resource base, which required at that time exploitation for a young and growing nation. As a result, the agencies took on these attitudes of exploitation and inevitably became sympathetic to the ever-present voice of the developers. It is no secret that the Department of Interior has had a special relationship with the petroleum industry. In this atmosphere, the public, whose desires are less well articulated, come off second best. It has been pointed out in the Senate Interior Committee report, a copy of which you may examine, that a more direct input of public opinion is essential to the democratic process. The need has in part become apparent in Congress, and one landmark act, the National Environmental Policy Act of 1969, was a major move in giving the public a direct input into agency decision-making. Needless to say what that act has done to much of resource development in this country. It's important to recognize that in our complex society, decisions are for the most part made outside the public sphere, and often in spite of public opposition. The impact of energy and natural resource decision-making points out the urgency of considering new institutional arrangements where these unorganized segments of society, you and I, be represented by spokesmen and supported by a staff with resources. The idea of ombudsman in government is not new. The present energy dilemma has emphasized the limitation of the present way many government institutions operate. Specific deficiencies show: 1, inadequate development of a foundation of information on energy resources and their production, and especially the side effects of their development. 2, because of the imbalance in the influence of various sectors of society, our public energy decision-making does not reflect society's preference, but rather special interests. 3, energy policy programs and regulatory decisions are made in separate offices, piecemeal, resulting in poor coordination and little possibility of balancing interrelationships. 4, regulatory responsibilities of many agencies are interwoven with their program responsibilities, which promote the resource. Whatever solution the future may hold for these and other problems, such as are related to energy, they will not be arrived at in time unless we, the public, mount our own exponential growth curve, a growth curve in self-education, public expression, and innovative involvement in the planning and decision-making process. Thank you.
Thank you, Jim, for those thought-provoking remarks dealing with the pitfalls and problems associated with our growing demand for energy and your program for coming to grips with these problems. I'd like to say, last but certainly by no means least, our last panelist to make his initial presentation is Dr. Thomas D. Wheelock, professor of the Chemical Engineering Department at Iowa State University. Prior to coming to Iowa State University, Dr. Wheelock worked as both a sales engineer and chemical engineer in industry, and during his stay at Iowa State University, he's also done consulting work with industry. In the area of research, his interest lies in the area of investigating fluidized bed reactors and their application to various chemical treatment processes, such as coal gasification, which is a potential source of energy supply. And without further ado, we'll turn it over to you, Tom.
Well, thank you, Howard. I'd like to have the lights dimmed so I can show a few slides. I think we need to be concerned today about our supply of natural gas. This chart, which appeared in Chemical Engineering Magazine last October, shows the potential demand and anticipated supply for natural gas starting in 1965 and continuing through the year 1985. Now, I think that what this shows is that the potential demand is far outstripping the supply. The supply and demand were pretty much in balance back in 1965, but by 1970, the potential gas demand was about 14% greater than the supply. And by 1985, the potential gas demand is going to be about 179% greater than the supply. Now, our supply curve for gas probably peaked out in 1970. And so now we're in a period of steady decline, whereas our demand curve continues to rise. Next. Well, back when man first appeared here on the surface of the earth, there was about 9 or 10 times as much energy tied up in the form of coal and lignite as in the form of natural gas or petroleum. This graph shows and compares the initial supply here on the surface of the earth. And you can see that coal was present in much greater amounts. Now, we're using up the gas and oil at a great rate. Fortunately, most of our initial coal supply is still intact. Now, this is data that was assembled by the U.S. Geological Survey several years ago and is attributed to King Hubbert of that agency. And it shows, plotted here, the annual production rate of natural gas in the United States from starting in the year 1900 and continuing through the year 2060. And from 1900 up to the present time, of course, natural gas supply and demand and production increased at an exponential rate. Every year, the supply and consumption increased by 6.34%. Now, we're at this point, and you see if we follow this exponential curve, we'd go right out the roof. Obviously, this is a physical impossibility, and Hubbert predicted that the production of gas would have to peak out, and he predicted that it would peak out in 1980. Well, you saw on that previous graph that it probably peaked out in 1970. So from here on out, it's a declining supply. Now, I think the most startling finding is that about 80% of our total gas supply will be consumed in only 65 years. This is, barely one person's lifetime. And to think that 80% of our gas will be used up within that span of time, I think is quite startling. The situation in the case of coal is much brighter. This graph shows the annual production rate of coal between 1800 and the year 2800. Now, the time scale here is much broader. This covers 1,000 years. So far, we've used the amount of coal which is represented by this the shaded area. Now, Hubbard has estimated that we could increase our production of coal for a number of years, perhaps for the next 200 years, before it would peak out and our production rate would start to decline. Now, there are two curves on this graph. One of them is a very conservative estimate. This reflects the coal fields that have been mapped and measured accurately. The other curve is a much less conservative estimate. But I think the important thing is that we have enough coal to last us for several centuries, whereas we only have enough gas to last perhaps a few decades. Now, the coal in the United States is widely distributed. This map shows where the principal coal fields are located in the United States. Now, of course, you've heard about the Appalachian coal fields. They're very famous, and a lot of our best coal comes from that area. In the Midwest, we have large coal fields underlying Iowa, Illinois, Missouri, Kansas. And, of course, in the West, we have some very large coal fields which are largely untapped. And we have lignite fields down in the southern part of the United States and also up here in the Dakotas. The character and quality of the coal vary a great deal from one coal field to another. Here in the Midwest, our coal tends to be of medium quality. It has a great deal of sulfur, a great deal of ash-forming material. In Appalachia, they have a high-quality bituminous coal, but it too contains appreciable amounts of sulfur. And it's only out here in the west, in the Rocky Mountain area, that you find coal that contains very little sulfur. And so today, you may have observed unit trains on the railroad passing through Ames conveying this coal from Wyoming to the Chicago area, where they need the low-sulfur coal. The fact that coal is widely distributed, I think, means that sometime in the future it'll be feasible to locate coal gasification plants in various parts of the country which will be close to consumption centers. For example, I wouldn't be surprised, but in the future we'd see a large gas plant in the Dakotas supplying gas to the Minneapolis-St. Paul area. We'll probably see gas plants in central Illinois supplying the Chicago area, and gas plants in West Virginia and Pennsylvania supplying the population centers of the East Coast. The transportation distances will be, of course, much smaller than they are at present for conveying gas from the Gulf Coast region to St. Paul or to Chicago or to the eastern seaboard. What about the technology? Some of you may recall that several decades ago, every city in the United States almost had a gas plant. In fact, we had a gas plant right here in Ames for making gas from coal. The type of gas that was produced was of very inferior quality. I don't think any of us would want to go back to that type of gas. So the gasification of coal in the future demands new and improved technology. Some of this is available today in Germany. The Lergi company of Germany has developed a process for converting coal into a substitute natural gas. Unfortunately, the German process has a few drawbacks. For example, it's not suitable for all types of coal. So in the United States today, we have a sizable research and development program which is aimed at developing new processes for converting coal into substitute natural gas. And there are at least 4 leading processes under development, which I have listed here: the high gas process, the CO2 acceptor process, the biogas process, and the synthane process. The synthane process is being developed by the U.S. Bureau of Mines, the high gas process by the Institute of Gas Technology in Chicago, this process, the CO2 acceptor process, by the Continental Oil Company, the biogas process by the Bituminous Coal Research Institute. Now, in addition to these processes for manufacturing high-quality synthetic or substitute natural gas, we also have another type of process being developed which would produce a low BTU fuel gas which would be used for the generation of electric power. You may have noticed within the last couple of weeks an item in the paper, a newspaper, saying that Westinghouse had been awarded a contract by the government to develop a low BTU fuel gas. Now this simply compares the characteristics of the old type of coal gas that we used to produce in this country with the new substitute natural gas that we need. Several decades ago, we produced water gas, which was primarily a mixture of carbon monoxide and hydrogen. It had a low heating value. It was produced in low pressure, rather inefficient processes. It was uneconomical to transport very far, and of course it would be incompatible with our present burners today. We couldn't use it in our furnaces and stoves without changing the burners. So what we need is a substitute natural gas which has essentially the same chemical composition as natural gas, which has a high heating value, just as natural gas has, which would be produced in high pressure, continuous processes, which would be economical to transport, and which would be compatible with present burners. To produce this type of gas from coal requires a very complex process. And I show here a schematic diagram of such a process which starts with mining the coal and then pre-treating it, gasifying it at high temperatures and pressures with steam. The gas would then have to be cleaned and be passed through several chemical reaction steps in order to finally produce the high-quality substitute natural gas we need. This simply shows some of the chemical reactions involved, and I think you can see that it's a very complex process. Consequently, it requires a great deal of development, which takes a long time and a lot of funds. Several gas pipeline companies have announced their intention to construct coal gasification plants, 2 of them in New Mexico, in northwestern New Mexico in the Four Corners area, 1 of them in central Illinois. Now, hopefully these plants may be constructed and ready to operate by the latter half of the present decade. These plants would utilize the German technology because we haven't yet developed our own technology. Each of these plants would be quite sizable. Each would be capable of producing about 250 million standard cubic feet of gas per day. Each would cost about $250 million. Each would consume about 400 to 500 train carloads of coal a day. At the same time, our own technology is developing. And this is being sponsored and supported jointly by the American Gas Association and the Office of Coal Research, which is in the Department of Interior. The primary thrust of this development program is a series of large pilot plants. So now we have a large pilot plant in Chicago designed to demonstrate the high gas process. There's another large pilot plant in Rapid City, South Dakota, designed to demonstrate the CO2 acceptor process. Another large plant is under construction in Pennsylvania to demonstrate the biogas process. This joint program is costing $30 million per year, with 1/3 of the funds coming from industry and 2/3 from government. Now, the idea here is to demonstrate these processes in a pilot plant scale, take the information that's developed in the pilot plant operations, use that to design a prototype plant which will be 1/3 of full industrial scale. This prototype plant will cost about $150 million, and perhaps it will be ready to operate by 1976.